In 1808, John Dalton, a British schoolteacher, introduced the atomic theory of matter, establishing a scientific basis for understanding atoms as the fundamental particles of matter. Dalton's atomic theory effectively explained several key scientific principles, including the law of conservation of mass, the law of constant composition, and the law of multiple proportions. These laws provided a framework for understanding chemical reactions and the behavior of substances. However, Dalton's theory did not account for certain phenomena, such as the electrical charging of materials like glass and ebonite when rubbed with silk or fur, which posed questions about the nature of electricity and matter. Insights into atomic structure began to emerge from experiments involving electrical discharge through gases. A crucial principle was established: like charges repel each other, while unlike charges attract. This principle became foundational in understanding the behavior of charged particles. In 1830, Michael Faraday demonstrated that passing electricity through an electrolyte solution caused chemical reactions at the electrodes, resulting in the liberation and deposition of matter. This finding suggested that electricity has a particulate nature, which was a significant step forward in the study of both chemistry and physics. During the mid-1850s, scientists, particularly Faraday, began to investigate electrical discharge in partially evacuated tubes known as cathode ray discharge tubes. These tubes, constructed from glass and containing two metal electrodes, allowed researchers to observe electrical discharge at low pressures and high voltages. By adjusting the gas pressure within the tubes, scientists could study the flow of particles moving from the negative electrode, or cathode, to the positive electrode, or anode. This experimentation was crucial in advancing the understanding of atomic structure and the nature of electricity. When a sufficiently high voltage was applied to the cathode ray tube, a current flowed through the tube, generating cathode rays or cathode ray particles. This flow was confirmed by creating a hole in the anode and coating the area behind it with phosphorescent material, such as zinc sulfide. When cathode rays struck this coating, a bright spot appeared, indicating their presence. This observation was pivotal, as it provided tangible evidence of the existence of these particles. The experiments produced several key observations. First, cathode rays originate from the cathode and travel toward the anode. Although the rays themselves are invisible, their effects can be detected using fluorescent or phosphorescent materials that glow upon contact. This principle is the basis for television picture tubes, where images are produced through fluorescence on screens coated with special materials. The ability to visualize the effects of cathode rays marked a significant advancement in experimental physics. In the absence of electrical or magnetic fields, cathode rays travel in straight lines. However, when subjected to these fields, their behavior aligns with that of negatively charged particles. This observation suggested that cathode rays consist of electrons, which are fundamental components of atoms. Importantly, the characteristics of these cathode rays do not depend on the type of electrodes or the gas present in the tube, leading to the conclusion that electrons are universal constituents of all atoms. This understanding significantly advanced the fields of chemistry and physics, providing a clearer picture of atomic structure and paving the way for future discoveries. The implications of Dalton's atomic theory and subsequent experiments on cathode rays laid the groundwork for modern atomic theory, influencing numerous scientific advancements. The realization that atoms contain smaller particles, such as electrons, transformed the understanding of chemical bonding and reactions. As research progressed, the role of electrons in chemical reactions and bonding became increasingly evident. Electrons are responsible for the formation of chemical bonds, which are essential for the creation of molecules and compounds. The transition from Dalton's initial theory to the discovery of the electron illustrates the evolution of scientific thought and the ongoing pursuit of knowledge in understanding the building blocks of the universe. The exploration of cathode rays not only enhanced atomic theory, but also led to the development of new technologies, including television and various electronic devices. The impact of these early experiments continues to resonate in contemporary science, underscoring the interconnectedness of discovery and innovation. The principles established through the study of cathode rays have influenced fields ranging from electronics to quantum physics. In summary, John Dalton's atomic theory laid the foundation for understanding matter, while the subsequent exploration of cathode rays revealed the existence of electrons, fundamentally transforming the scientific landscape. This journey from theoretical concepts to practical applications highlights the significance of inquiry and scientific exploration in unraveling the mysteries of the universe. The study of atomic particles remains a dynamic field, with ongoing research revealing more about the complexities of matter and energy. As scientists delve deeper into the atomic realm, the foundational work of pioneers like Dalton and Faraday continues to inspire and inform modern scientific endeavors. The quest to understand the nature of matter is far from complete, and new discoveries are continually reshaping the landscape of science. In conclusion, the atomic theory and the discovery of electrons represent significant milestones in the quest to comprehend the nature of matter. These developments have shaped the future of science and technology for generations to come, illustrating the profound impact of scientific inquiry on human understanding and innovation. The legacy of Dalton and Faraday serves as a reminder of the importance of curiosity and exploration in the pursuit of knowledge. In 1897, British physicist J.J. Thomson made a groundbreaking advancement in the field of physics by measuring the charge-to-mass ratio of the electron using a cathode ray tube. This experiment marked a pivotal moment in the understanding of atomic structure and the nature of electricity. Thomson's innovative approach involved applying perpendicular electric and magnetic fields to the path of electrons, allowing him to observe their behavior under different conditions. When only the electric field was applied, the electrons deviated from their original trajectory and struck the cathode ray tube at a specific point. This deviation was a clear indication of the influence of the electric field on the charged particles. In contrast, when only the magnetic field was present, the electrons hit the tube at a different location, demonstrating the distinct effects of magnetic forces on their motion. By meticulously balancing the strengths of the electric and magnetic fields, Thomson was able to redirect the electrons back to their original path, enabling them to strike the screen as they would in the absence of any fields. Thomson's observations led him to identify three critical factors that influence the deviation of electrons in electric and magnetic fields. The first factor is the magnitude of the negative charge on the particle. Thomson reasoned that a greater charge would result in a stronger interaction with the electric or magnetic field, leading to a more significant deflection. The second factor is the mass of the particle. Lighter particles experience greater deflection compared to heavier ones. Finally, the strength of the applied electric or magnetic field plays a crucial role. As the voltage across the electrodes or the strength of the magnetic field increases, the deflection of electrons from their original path also increases. By conducting precise measurements of the deflections observed in the presence of electric and magnetic fields, Thomson was able to calculate the charge-to-mass ratio of the electron, denoted as E/μ. His calculations revealed that this ratio equals 1.758820 turns 10 to 11 kg. Here, E represents the magnitude of the charge on the electron, while me denotes the mass of the electron in kilograms. Since electrons are negatively charged, the charge is expressed as E. The significance of Thomson's work extended beyond the charge-to-mass ratio. In the following years, American physicist R.A. Millikan devised an experiment known as the oil drop experiment to determine the charge on the electron with even greater precision. Millikan's experiments involved balancing the gravitational force acting on tiny oil droplets with the electric force exerted by an electric field. Through careful measurements, he found the charge on the electron to be approximately 1.610 C. This value closely aligns with the currently accepted charge of 1.602176 for 10^19 C. Combining Millikan's findings with Thomson's charge-to-mass ratio allowed scientists to calculate the mass of the electron, which was determined to be approximately 9.141031 keys. The exploration of cathode rays and the properties of electrons did not stop with Thomson and Millikan. Modified cathode ray tubes led to the discovery of canal rays, which are streams of positively charged particles. Unlike cathode rays, the mass of these positively charged particles depends on the nature of the gas present in the cathode ray tube. These particles are essentially positively charged gaseous ions, and their characteristics vary based on the gas used. The charge-to-mass ratio of the positively charged particles also depends on the specific gas from which they originate. Some of these positively charged particles carry a multiple of the fundamental unit of electrical charge, indicating the diversity of ionization processes occurring within the tube. Furthermore, the behavior of these positively charged particles in magnetic or electric fields is opposite to that observed for electrons or cathode rays, highlighting the complexity of charged particle interactions. Among the positively charged particles, the smallest and lightest positive ion was derived from hydrogen and was named the proton. This fundamental particle was characterized in 1919, marking a significant milestone in the understanding of atomic structure. The identification of the proton provided insight into the composition of atomic nuclei and the nature of positive charge. As research progressed, scientists recognized the need for an electrically neutral particle to complete the picture of atomic structure. This led to further investigations, and in 1932, physicist James Chadwick discovered the neutron. Chadwick's discovery came from bombarding a thin sheet of beryllium with alpha particles, resulting in the emission of electrically neutral particles with a mass slightly greater than that of protons. The identification of neutrons was crucial for understanding the stability of atomic nuclei and the forces that hold them together. The combined efforts of Thomson, Millikan, and Chadwick laid the foundation for modern atomic theory. Their discoveries not only enhanced the understanding of the electron, proton, and neutron, but also revolutionized the field of physics. The charge-to-mass ratio of the electron, the precise measurement of its charge, and the identification of protons and neutrons have all contributed to the comprehensive model of the atom that underpins much of contemporary science. This foundational knowledge continues to influence research in fields ranging from chemistry to particle physics, shaping the understanding of matter and the universe. The understanding of atomic structure has significantly evolved through various models proposed by scientists over the years, with notable contributions from J.J. Thomson and Ernest Rutherford. Each scientist provided a unique perspective on the arrangement and behavior of charged particles within an atom, leading to a deeper comprehension of atomic structure. In the late 19th century, J.J. Thomson introduced the plum pudding model of the atom. This model depicted the atom as a spherical entity with a radius of approximately 10 meters. Thomson suggested that the positive charge was uniformly distributed throughout the sphere, while negatively charged electrons were embedded within this positively charged pudding. This arrangement was theorized to create a stable electrostatic configuration, similar to how plums are distributed in pudding. This visualization helped conceptualize the atom's overall neutrality as the positive and negative charges balanced each other. Despite its innovative approach, the plum pudding model faced challenges when confronted with experimental evidence. While it provided foundational insight into atomic structure, it could not adequately explain the stability of atoms or the results of later experiments. Nevertheless, Thomson's work was groundbreaking, earning him the Nobel Prize in Physics in 1906 for his theoretical and experimental investigations into the conduction of electricity by gases. The landscape of atomic theory shifted dramatically with the experiments conducted by Ernest Rutherford and his colleagues Hans Geiger and Ernest Marsden in the early 20th century. Rutherford's alpha particle scattering experiment marked a turning point in the understanding of atomic structure. In this experiment, a stream of high-energy alpha particles was directed at a very thin foil of gold, approximately 100 nanometers thick. Surrounding the foil was a circular fluorescent zinc sulfide screen, which emitted a tiny flash of light whenever an alpha particle struck it. The results of Rutherford's scattering experiment were unexpected and profoundly influential. According to Thomson's model, the mass of each gold atom in the foil should have been evenly spread throughout the entire atom. Therefore, it was anticipated that the alpha particles, possessing sufficient energy, would pass through the foil with minimal deflection. However, the observations revealed a different reality. Most alpha particles passed through the gold foil undeflected, indicating that the majority of the atom is composed of empty space. Additionally, a small fraction of the alpha particles were deflected at small angles, suggesting the presence of a concentrated positive charge within the atom. Most strikingly, a very few alpha particles, approximately 1 in 20,000, were reflected back nearly 180 degrees. This significant deflection implied that the positive charge within the atom was not uniformly distributed as Thomson had proposed, but rather concentrated in a very small volume. Based on these observations, Rutherford drew several critical conclusions regarding atomic structure. First, he concluded that most of the space within an atom is empty, as evidenced by the majority of alpha particles passing through the foil without any deflection. Second, the deflection of some alpha particles indicated the existence of a dense, positively charged nucleus that repelled the positively charged alpha particles. This nucleus must occupy an incredibly small volume compared to the overall size of the atom. Rutherford's calculations revealed that the radius of the atom is about 10 meters, while the radius of the nucleus is approximately 10 to 15 meters. To illustrate this vast difference in scale, one can imagine a cricket ball representing the nucleus. In this analogy, the radius of the atom would be about 5 kilometers. This stark contrast highlights the remarkable emptiness of atomic space. In light of these findings, Rutherford proposed the nuclear model of the atom. According to this model, the positive charge and most of the atom's mass are densely concentrated within a small region known as the nucleus. The nucleus is surrounded by electrons that move rapidly around it in defined orbits, akin to planets revolving around the Sun in a solar system. This model not only provided a more accurate representation of atomic structure, but also established a framework for understanding the forces that hold the atom together. Rutherford's nuclear model emphasized the electrostatic forces of attraction between the negatively charged electrons and the positively charged nucleus. This balance of forces is crucial for the stability of the atom, allowing it to maintain its structure despite the inherent repulsion between like charges. The transition from Thomson's plum pudding model to Rutherford's nuclear model marked a significant advancement in atomic theory, laying the groundwork for future discoveries in atomic physics and chemistry. In summary, the evolution of atomic models, particularly through the contributions of J.J. Thomson and Ernest Rutherford, has profoundly shaped the understanding of atomic structure. Thomson's plum pudding model introduced the concept of charge distribution within the atom, while Rutherford's nuclear model provided a clearer picture of atomic organization and stability. Together, these models illustrate the dynamic nature of scientific inquiry and the continuous quest for knowledge in the realm of atomic theory.